All right, let's go ahead and take a look at question number 5 in this video. Now, with this one, it has an x out in front, a variable expression out in front of the square root part. This makes me suspicious it's arcsecant. Wait a minute, why isn't it letting me write? Okay, there we go. Looks like it's arcsecant. Okay, but we'll see, we might need to make a little bit of adjustment to make it match. It's got, if you'll notice, it's got the variable expression in the correct spot. Okay, it's first, it's u squared minus a squared, so it's got that right. The problem is going to be that this isn't just an x squared, it's an x to the fourth. So you'll see what I mean in a minute. So my a squared comes from the constant, the 4. So I know a is going to be the square root of that, which is 2. And then my u squared is going to be x to the fourth. So u would be the square root of that, which would be x squared. Okay. So then if I do the du, I will get 2x dx. Okay. And then we're going to hold off a minute on what we need to do with that. Okay. Because one of the issues is that when I'm looking at this, I can get that written to be x squared squared minus the 2 squared. So I see my u and my a that I'm going to need. But then according to that formula, let me write that formula for you right here where you can see it. So according to that formula, if you're integrating 1 over, when you're doing your arcsecant one, that formula is 1 over the u, and then it has the square root of u squared minus a squared, okay, du. So see, whatever that is there, I need that out front. So here I have a x squared. So instead of just an x out here, I'm going to go ahead and get a different color. So instead of just an x out in front, which is what I have currently, I'm going to need an x squared. So currently I have an x, but I really need that to be an x squared. So we're going to manage that by putting an x in there so that we get the x squared we need out in front. But if I do that to the denominator, I'd have to do that to the top. Okay. Also, we still have dx here to the side. So this one was a tougher than usual one because of that. Okay. All right. So now what I'm going to do is kind of organize it a little bit before we do our substitution. So I'm going to take my 1. I'm going to put that's really an x. I'm going to put that x over there with the dx on the outside. Then I'm going to have 1 over x squared and then the square root of x squared squared minus 2 squared. Okay. All right. So now I kind of like the look of it. Now it's starting to feel a lot like that problem right there. It's just I'm going to put my u's into it. So the x dx, I'm going to be able to put in something related to du, but you got to watch it because notice here is x dx. We'd have to do 1/2 du to get the x dx. Okay, so I'm going to replace the x dx with 1/2 du. Okay, there at the end. And then this will be 1 over the u, and then this will be square root of u squared minus 2 squared. Okay. All right, now that's fitting the formula precisely, this part. So I'll bring the 1/2 down. Then I'm just going to use that arcsecant formula. It says to do 1 over your a value, so that's 1 over 2. This 1/2 came from here. Then 1 over your a, and then you're going to do arcsecant of u over your a, and the u should be an absolute value plus c. So that's 1/4 arcsecant, and what's going in place of the u is an x squared, so I don't really need absolute value because that will always be positive, divided by 2 plus c. Okay. All right, so I wanted to do at least one that had an arc secant in it. And the one I did is harder than the typical one, only because this was a 4, not just a 2, or because out here we didn't already have an x squared, which we would have needed. Okay. Now this one looks weird because of the fact it has an e in it. Okay. All right, but let's take a look at this. On this one, I'm going to think of it kind of like this. All right. That e to the 2x is going to have something to do with the e to the 4x, we'll notice in a minute. I'm going to do this one using arctan because I don't see a square root. So I can think of it as 1 over 2 squared plus e to the 2x squared. Because remember, when you have a power raised to a power, you can multiply 2x times 2 to get your 4x. And then I'm going to keep that e to the 2x dx here to the side. So that's what I'm trying to integrate. I'd like to go ahead and show you that you could have done a squared was 4. So a would be square root of 4 or 2. And u squared is equal to e to the 4x. So u would be the square root of that, okay, which would have been e to the 4x raised to the 1/2 power, or e to the 2x. Or you could have just thought, what could I raise to the second power to get that e to the 2x? Okay, now once you have that u equals e to the 2x, make sure you do the du of that. It would be e to the 2x times 2. Okay, and we don't have a times 2 out here. So we're going to get rid of that 2 by doing 1/2 on both sides. Okay, then this becomes the integral of 1 over 2 squared plus u squared. And in place of e to the 2x dx, I'm putting 1/2 du. So let me just keep the 1/2 out in front and the du there at the end. Then this is an arctangent problem. And with arctangent, you do 1 over your a. Okay. We already had a 1/2 though, so I need to bring that down too. And then it's going to be the u over 2 plus c. So our answer should be 1/4 arctan of e to the 2x over 2 plus c. Okay. All right, now these two problems are definite integrals. All right, let me go ahead and do number 7. And what we're going to do first is just get this part, just the integral, the indefinite integral figured out. And then we'll come back and do the definite integral part. So let's just think about this part. So I kind of like what I see in a way. I'm trying to get it to look like one of these, and I'm pretty sure it's going to be an arcsecant because I see a radical, and then there's also that x out in front of it. So I'm thinking about it as the square root of 2x squared minus 3 squared, okay? And I think by now you can do that without a lot of effort. I think you can see that the a would have to be 3 and the u would have to be 2x. Okay, and then if the u is 2x, then du would be 2 dx. So I'll need to get rid of that 2 to be ready to make a substitution on that piece. All right, then we've got this x out in front, which isn't quite what I need it to be, is it? Okay. I'll put the limits back on when I'm getting ready to do it, but I'm not ready to do that yet. So do you see that what I have here is a 2x, u is 2x, So this should be 2x. So we're going to do what we did on an earlier one. I can put a 2 there as long as I also multiply by 2 there. Okay. All right. So now I'm going to get things so they look like the arc secant problem. So I'm going to pull this constant out in front, this 2. And then what I really have now is what I wanted, which is a u and then square root of u squared minus the 3 squared. And then in place of the dx, I'm going to put a 1/2. So let me put the 1/2 out here with this and a dx. Okay. So I get what I'm trying to integrate is 1 over u square root of u squared minus 3 squared. Oops, I said I was going to do it, but then I didn't. So I replaced the dx with 1/2 du. Okay, so that's what I'm trying to integrate. And then the 1/2 times 2 would have canceled out. So when I go to integrate that, I'm going to get an arc secant situation. An arc secant tells me I need to, or the way you do an arc secant is you do 1 over your, where am I? There we are. So you're going to do 1 over your a value. So that would be 1/3. Okay. And then arc secant of your u in absolute value divided by your a value plus c. Okay. Now, here's where we've got to realize that we're really not doing indefinite integrals right now. Okay, that's what it would be if we did the indefinite integral. But we actually have these limits of integration here. These are with respect to x. So if I wanted to, what I could do is evaluate this, and instead of using the limits of integration they gave me to evaluate it, what I could do is figure out what those limits of integration are with respect to u. And where I'm going to do that is right here, or how I could do that is right here. So if one limit of integration is 3, and that would be an x of 3. So if x were 3, then it tells me that u should be 2 times that, or 6. So the top number in terms of the u would be 6, okay? And then the bottom number was an x of square root of 3. So the u would be 2 times that, or 2 square root of 3, okay? And so you could do that, or, and I'll go ahead and write it off to the side, or you can convert back to x's, and putting the x's back in, you would have 2x over 3, and then you would evaluate from the original limits from square root of 3 to 3, okay? Okay, so you can do either of those. All right, let me go ahead and move this down a little bit. So you can treat it either way. It's still a pretty tough problem because of it having a lot of trig in it. So when I put the 6 in, up here on top, the 6 over 3, and then I go and I put in the 2 square root of 3 over 3. I've got to understand what the arc secant is really asking me to find. And I think that's what makes this one so hard, is the trig, not the calculus so much. So here I have arc secant of 2 I'm trying to figure out. And here I have the arc secant of 2 square root of 3 over 3. So to figure this out, you really have to get what arc secant means. What we really need is the angle whose secant is 2. And there's another thing that's hard about it, and that has to do with arc secant and what the range of arc secant is, like where you can choose these values. So it has to be an angle that's within the first or second quadrant. So it has to, for arcsecant, it needs to be an angle here. Okay. So you have to think about secant is the same as 1 over cosine. So angle whose secant would turn out to be 2 would be the same as the angle whose cosine. So cosine of some angle would equal 1/2, the reciprocal of that. So I have to think about the angle whose cosine would be 1/2, and that would be right here. And that would be at 60 degrees, which is pi over 3. This one is asking me for the angle whose secant is 2 square root of 3 over 3, which means the cosine of the angle would have to be the reciprocal of that. And if you go through and simplify that, it turns out to be 3. If you wind up doing the top and bottom by square root of 3 over 3, you get 3 square root of 3 over 2 times 3 over 6, and then you're able to simplify that. Now, square root of 3 over 2 you should recognize as being the cosine of the pi over 6 angle. Okay? So this would be theta equaling pi over 3. Here it would be theta equaling pi over 6. Okay? All right, so I know this is a pretty tough one because of it being arcsecant and having to think backwards to figure out what they're asking you for. Okay, this is probably harder than you'll see on the final exam for sure. So this would be 1/3 of pi over 3 minus 1/3 of pi over 6. Okay, and so that would equal pi over 9 minus pi over 18, which would equal pi over 18. Okay, so there's several things about that were very understandably tricky. It did look like an arcsecant from the start, so I think that's understandable, but you did need to adjust because you were missing the 2. Okay. And then the next tricky thing after that came in when you're trying to figure out how to find the answer to this. And that's because sometimes we're not so great at our trig, and this is on the harder side of the trig stuff you have to do. Okay. All right, and then one last problem. This one's not too bad. I'm just going to need more paper, so let me get to a new page. So on this one, you see how there's no radical? So it's probably going to be an arctangent. Okay. And so on that one, I want it to look like an arctangent problem. Before I have to do my evaluating and all, I'm going to just think of the indefinite integral. So it's sine x squared. It's 1 squared minus 1 squared plus sine x all squared. I'll move the cosine dx off to the side. Cosine x dx off to the side. We'll be evaluating it later. I'm not going to put the limits on it and all right now. Okay. So I'm letting the a, or I can see the a would be 1, and I can see the u would be sine x. Then du would be cosine x dx, which means that cosine x dx can be replaced with du, and I'll put a u squared there. Then it matches perfectly to the arctan function, which says I need to do 1 over my a value, which is 1, and then arctan u over my a value, but my a value is 1. So arctan, it'll be arctan of the u value, and that was sine x. Okay. Oh, let me not do sine x. I'll show you that if you want later, but let's just keep it a u. and then change our limits of integration. So it'll be arctan of u, but I'm not going to be evaluating. If I'm going to leave it with a u, then the limits of integration are not from 0 to pi over 2 like they are here and here. Once I change it to a u, what I could do is use this formula right here to find out what happens when x equals 0. If x equals 0, u would be sine of 0, which is still 0. If x equals pi over 2, then u would equal the sine of pi over 2, which would equal 1. So that means I could evaluate this from 0 to 1. The limits would be 0 to 1. Now, if I didn't want to do that, I could have gone back to putting in my u, and then I would have had to evaluate from 0 to pi over 2. Okay. All right, so if we did make that switch, then I need to evaluate, I need to do the definite integral part. So I'm going to plug in a 1, arctan of 1 minus arctan of 0. Okay, so let me just write what you should be thinking. You need the angle whose tan is 1, and the angle should be something in the first or fourth quadrants. And here I need the angle whose tan is 0 there. Okay. So remember that when you're at 0 degrees, sine is 0 and cosine is 1. That's where you would be to get an angle whose tangent is 0. Okay. So this one, the arctan of 0, that would be 0 because you'd be right here. And then to get the tangent to be 1, you'd have to be where sine and cosine were the same, and that would be here where you have square root of 2 over 2 for both. So tangent would be 1. So that's at pi over 4. So your final answer on that one should be pi over 4. You won't be expected to do definite integrals on the final, and I'm not asking you these questions on the test. All right, that's it. Please tell me that I recorded this.